Welcome to the AIP Open Seminar. Um, Here's some important information about the seminar. Its reproduction is prohibited. Reproducing all or any parts of the content is prohibited. The seminar will be recorded and you can see the video later. And if you have any questions throughout the talk, keep putting it in the Q&A tab, and we'll be taking questions after every subpart of the talk. Okay, there are other open seminars that will happen in the coming weeks, and please check them out and attend them. Very exciting work that's going on at Rick and AIP is being showcased through these AIP Open Seminar. So today's open seminar is about our team, Approximate Bayesian Inference. And my name is Mohammed Imtiaz Khan, and you can call me MT, and I am the team leader of the group. And we'll be basically summarizing past work that has been done in the last 4 years, and also telling you about some recent works and some upcoming works from our group. Okay, so I will start by giving you a big picture overview of what we do. So our goal, like many machine learning people, is to design artificial intelligence systems that can learn like living beings, like human beings. And when I say that, what I mean is that we want a system that can learn and adapt quickly throughout their lifetime. And if you've seen my talks before, you've probably seen this video. This is how I like to motivate this point about learning like a human being, living being. This is my daughter, is 6 months old. She has very little idea of what is going around her, um, in her environment, but slowly she's figuring out what she likes and what she doesn't like through some random exploration. It seems random at first, but if you give her enough time, so this is after 6 months, she figures out what she likes, and she's now like really interested in the fretboard, the sound where it's coming from, and she's generating that data. So this is an amazing thing about human beings and also other living beings, that they can, through limited interaction with their environment, can figure out their own preferences in the world and have a reasonable understanding of the world so that they can do the things that they want to do in their life. And they don't stop there. So this is after 2 months when she is moved on from ukulele to a guitar, and guitar is a bigger instrument, but she has still somehow figured out how to get that sound that she was producing with ukulele. So this is the motivation that I usually give, is that people can learn throughout their life, and they do so by just interacting with the environment little by little. And they do so even when the environment around them changes. But machines, the state of the art that we have, for example, deep learning, we don't have that kind of mechanism, learning mechanisms. And usually the data is assumed to be all there in a bulk fashion. All the information in the world that I need to learn, it's all there in front of me. So the world is very stationary, and there is very clear differences between the two types of learning. And our goal in our group is to bridge the gap between these two types of learning, so design methods that can do that. And we are Bayesians, so we look to Bayesian principles to guide the design of such machine learning algorithms. And it's because human learning is, there's a lot of work in many fields like psychology and economics and social science, where Bayes rule and Bayesian learning has been shown to mimic the kind of learning that's done by rational agents. And our research lies on bringing this type of flavor to machine learning world, so that we can bridge the gap between the human learning and the deep learning using Bayesian principles. So our group consists of a variety of people, and you can actually see more about the activity of our group in this newly launched webpage. So I'm the leader of the group, and we have uh, Pierre Elkir, who's also a quite senior person in the Bayesian from the Bayesian statistics world. We have two postdocs who have recently joined. They're still working from Europe because of coronavirus. Janma works on structure prediction. Thomas is an expert of optimization and computer vision. Wu is a PhD student with me who works at UBC, and he used to be a part of the group full time here a few years ago. And Dharmesh, today he will give a talk today, and he's a research assistant. And then we have a couple of sort of part-time students and remote collaborator. Well, they were supposed to be interns and visiting students, but because of coronavirus, they're not here with us. Uh, and today, me, Pierre, and Dharmesh will be giving a talk. And hopefully, throughout the year, you will see talks by the rest of the members showcasing their own research. Okay, so I hope that this gives you an idea of how the group is structured. Let me just tell you about today's agenda. So, what we want to tell you uh, are these Bayesian principles that we have worked on in the past and are working on right now. And I'll start with a background on why this is useful, which is basically uncertainty. And then from there, I'll go to how the uncertainty can guide learning algorithms. So there's something that we have done in the past is to derive learning algorithm from Bayesian principles. And so this will be my work, and then this will be like my talk, and then we'll move on to the current work that we are doing, which is about knowledge. So we are working on knowledge representation, transfer, and also on collection. And Dharmesh will start with representation on memorable experiences. Then I will talk about its application to continual learning. And then Pierre will talk about meta learning and some theoretical results related to that. So that's the plan for today. Okay, so we'll take breaks every 30 minutes or so. So if you have questions, just keep putting them in the Q&A box, and we'll be answering them as we go. Thank you. Okay, so let me start with a question to motivate why people should be Bayesian and why should we be thinking like Bayesians. Here's a question that I like to ask people. So I've shown you a set of data points here, and this is the square class and this is the circle class. And what I've done is I have drawn two lines that classify the data points. And if this meeting was in person, I will ask you to raise your hand and answer the question, which is a good classifier. And now we can't do that in this um, virtual talk, uh, but I can sort of guess what most people think. So most people would pick the blue line because it seems like a more stable line because it's somehow going through and there's more margin around the line. So it seems a little bit a better choice. And that's what machine learning sort of tells us, that when you're given data, well, you should pick something that's kind of more stable. But if you think about non-stationary setting and lifelong learning kind of setting, where you don't know where the next data set is going to come from, it's very difficult to make this choice. Okay, so just to give an example, this is an adversarial setting where I'm making up this data set that's making the blue line be a bad line, right? So the square class appears here, and the blue line is not classifying it well, right? So my point is not that the blue line is a bad line or red line is a bad line, but rather in this situation, when you're young, when you only have limited experience of the world, you don't know what's coming next. So when you're in this kind of non-stationary lifelong learning, kind of setting, then it doesn't make sense to make a firm choice, to be so confident about your choice. And that is the point of uncertainty and being Bayesian, is that if you're really sure right now that the blue line is a good line, then when you observe the next set of data, you pay a huge cost. And you'll have to kind of do retraining, and you have to go from here to there, right? Because red line is the better line. And you can avoid these kind of costs by thinking about uncertainty, that when you're in this time, you actually had a very limited information about the world. You didn't know what kind of data labels would be coming in the rest part of the input space, right? So there's a lot of gaps between the data, and uncertainty is basically thinking about the gaps, thinking about things that are far from the data. How much do I know and how much do I not know? So my point is that if you don't know something, that can come to hurt you later, and that's why uncertainty matters. Now, what we do with Bayesian principles, that the point is that we will estimate a distribution over the parameters. So instead of just having one line, blue line or red line, we'll now have many lines that are sort of sampled from a distribution, and we try to learn that distribution. So this is the key idea of Bayesian principle. Here in this example, I've shown you simple logistic regression that's without an offset. It's a very, very simple model. And if you're frequentist, then you will have only one line. So this is this blue line trained with Adam. And if you're Bayesian, you would estimate a distribution instead. So in this case, we're doing a Gaussian distribution over the parameters, so over the lines, and we're generating samples from it. So the thick red line is the mean, and then the pink lines are the samples from it. Right. So this is based on this paper that I will be talking about it shortly. So I hope you get the point that instead of having just one line, now I'm trying to fill the gap between the data. So I have a range of lines, and if I choose a more flexible distribution, I'll cover more of the space. So that'll be a better approximation to the posterior distribution, is what we call in the Bayesian learning. Now, this can also be done for neural network, and that is even more important because you can draw lines more flexibly. So your distributions can be actually very, very complicated, and they have to go through all these gaps of the data. So the point in all of this is basically to fill in the gaps between the data, to think outside the data, to think outside the knowledge that actually the data is telling you, and think about where you have not observed things. So it seems like a hard thing to do, but it's actually the right thing to do. So this is an example to just to give you a sense of the real kind of application that this kind of problem can have. So here it's an image, and our goal is to segment the image into several parts. So it's like a road and the sidewalk and buildings and the sky and tree, things like that. And if you do, a deep learning model and you try to predict using that, it does quite a good job of prediction. But if you look closely, you see that some parts are kind of missed. So the sidewalks are classified really badly, and there's some places where wrong prediction. Now, if you have a self-driving car or something, and then you try to use these predictions, then you may do really poorly, because you might be driving on the sidewalk and you hurt some people. So it's kind of mission critical setting. These uncertainties are important. Here's two example. Again, uncertainty is a very broad term, and there are many ways to do uncertainty, and Bayesian is just one way. And here we're showing you two types of uncertainty taken from a Bayesian method, but you can have other types of things as well. So it's kind of telling you that the predictions you shouldn't trust these predictions, because we're not very confident about it. The other advantage that you can get is that because you're sampling from a distribution, you're learning a distribution and then using the samples to form averages. The predictions are usually, less confident, but also they're smooth. They generalize better, or they're expected to generalize better, at least theoretically. So like just a toy example here, where if you just use one neural network, the lines are very, very, wiggly. And if you had many neural network and you predict using them, and if you just average them, then the lines are smoother. So this kind of predictions are more stable. So this figure is actually generated by something called marginal likelihood, and I will be talking about some of the methods that are used to compute this. Okay, so my point in all this in the background is to say that we should start thinking about, we should be estimating distributions over parameter, not just a single parameter setting. And that's what being Bayesian is about. And the main principle behind it is to think away from the data and not to be really in love with the data too much, which is kind of a different way of thinking, right? So you start with a distribution that's actually not only paying attention to the data, but also trying to fill the gap between the data, between our understanding of the world. What I will talk about now is that when you start learning distributions, it might seem like you are doing something more or additional extra hard work. Uh, but it turns out that if you have this thinking of Bayesian, you know, uh, of estimating the distribution, it turns out that you can derive the strategies that are not estimating distributions as a special case. Okay, so thinking about distribution is strictly more general, not only in the philosophical sense, but also many learning algorithms that you deploy in the non-Bayesian world, they can be seen as a special case of the Bayesian learning, the algorithms that are doing Bayesian learning. Okay, so I will try to talk about this thing. This has a kind of a summary of some of the work that we have done in the last 4 years, basically deriving learning algorithm from Bayesian principle. Okay, so let me just make this notion of estimating distribution a little bit more concrete. So in deep learning, basically what you usually do is you have a model, some parameters of the model. So here I denoted with theta, and then you write a loss function, and then you try to minimize that loss function using some kind of algorithm, right? What I'm actually saying in the pictures that I showed in the beginning is that I should be estimating distribution over the parameter. So here I've denoted this by Q, and this distribution belongs to some class. So this is like, we call it posterior approximation. This could be the set of all probability distribution, or it could be a subset, like a set of Gaussian distribution, something of that sort. But what you're doing here basically is that you're minimizing the expected loss. So you're saying that I should not just look at the loss at one theta, but I should sample, I should generate many candidate lines. And then maybe some of those lines will be going, at arbitrary places, but all of them should sort of fit the data well. Okay, so I'm looking at the average over those lines. And that's how you get this stability of, less overfitting, less wiggly lines. But I want these lines also not to lie on top of each other, right? So I don't want them to be redundant. I want them to be diverse. So we put this entropy as a regularizer over this distribution, which is essentially saying that the lines should go to different places. They should not all just be on top of each other. Now, this formulation, if you write it and if you set this Q to be set of all probability distribution, then that's actually equivalent to doing Bayes' rule. So this was actually originally it was written a long time ago, but this is a good reference to look at in 1988. And if you also get very interested in it, look at work of E.T. Jaynes, which comes from 1957. It really talks about these general principles, the maximum entropy principle, where we are trying to maximize the entropy subject to some constraints which come from the data. So you're trying to make sure that the uncertainty reduces as you get more and more data. Now, this looks more complicated than that, but if you actually think a little bit more, it's not. So just to give you an example, I've shown you, so here you see this is the loss L of theta. So I've set, okay, so this will become clear quite soon. So this is the loss. So think of this as loss, and you have multiple local minima here. So it's a non-convex problem. And what the Bayesian objective is doing here, I've chosen Q to be Gaussian. So then I have mean and the standard deviation for this loss. And I plotted the loss function as a function of that, the two parameters of the posterior approximation. Um, Now, what you can see here, what becomes clear if you actually look at the slices of this loss. So what is actually happening here is that I'm increasing the standard deviation. Okay, so this loss, as I increase the standard deviation, what happens is that lots of these local minima that you have, they kind of start to disappear. And only the ones that are more stable, that are more wide, those are the ones that are kind of stable, right? So you see why this objective would be more stable and more robust than that objective is because it's trying to smooth the loss and remove spurious local minimum, right? But of course, it makes sense when you're able to choose the standard deviation properly. And that's basically what this objective is trying to do, trying to get the right diversity so that you're going between the gaps in the data, but also fitting the data well. I hope this is clear to you. And what I wanted to say is that this formulation, why I call it Bayesian principle and not Bayesian inference, is because this is a general concept and more general than what many times you study in basic books, like in Bishop's book. You will see a lot of like Bayesian inference, but this idea and this principle is a lot more common than that. It's used in stochastic search, in inference, in graphical models. It's also used in robust optimization, perturbed optimization, smooth optimization, continuation method, homotopy, lots of methods that fall within this category. And then also in online learning, it's known as pack-based methods that Pia is going to talk about in the end. And also reinforcement learning. If you think of Q as the policy, you can see some of these Bayesian principles in action. Okay, so the word Bayesian principle is a little bit more general than Bayesian inference, and that's why I use it. And I hope that this has motivated you to see that many problems can be actually seen as following this Bayesian principle. Now, when Bayesians talk about these ideas, then other people say, well, this is like a philosophy, and it probably is not very practical. But this part of the talk, I just kind of give you a quick glimpse into why this is not a theoretical construct, but rather many practical learning algorithms that you use in practice are all kind of a special case of this Bayesian learning. So what I will show you is that deep learning algorithms that are usually in from this side of the world, where you're minimizing the loss and computing a point estimate, they follow this kind of rule. But you can actually write a learning rule that optimizes this Bayesian objective. And there, if you change this Q, if you change the posterior approximation to be of different form, then you can recover these variety of learning algorithm as a special case. Okay, so um, essentially this work we started here. I mean, actually, I joined here and I submitted this paper in 2016. And this sort of forms the basis of everything that happened afterwards. And all of this is summarized. Well, most of it is summarized. This paper is still not finished, but it's there on my webpage, and you can see some of these results that I'm talking about right now. So what essentially we did is that we said, well, let's write an algorithm. We call this Bayesian learning rule. It's sort of an extension of Bayes' rule. But here we are focusing on a specific type of exponential family approximation, so something like a Gaussian, and we're learning the parameter of it. So this is natural parameter. And when you're learning the parameter, you're taking the gradient of this objective. So you're maximizing the Bayesian objective with a slight tweak that you're taking the gradient with respect to a slightly different parameterization. It's expectation parameter. And it actually turns out to be something motivated from information geometry. It's called natural gradient. You take the gradient of this objective and you update the parameters. Okay. Now this might look a little bit more, like there's some details here on what is going on, but the key point to remember is that if you choose the Q appropriately, you can get this sort of algorithm as special cases. Okay, so that's the point of this Bayesian principle. Okay, so just to give you a little bit of idea of how this is actually done, it's pretty straightforward. So let's say we want to derive gradient descent from this Bayesian principle, which has no preconditioner. So just taking the gradient of the loss and minimizing it. Then you can choose Q to be a Gaussian with fixed covariance. It doesn't matter what the covariance is. It just kind of disappears in the step size. So I've chosen to be 1 here. Then what you do, you write the natural parameter and the expectation parameter. These are all straightforward calculations. You can see the details in here. And you write the entropy because entropy is in the objective. But you see that the entropy is constant. So it just kind of disappears from here. And because mu is just m and lambda is just the mean, so you just write it down and you see that this already looks very similar to this. Right? And now, because you want a non-Bayesian method, so you want to estimate only one point estimate and not the distribution, you can sort of make certain approximation here. So the most common one is something called delta method that just approximate the expectation by a point, so just the mean. And if you choose that, then it becomes the gradient descent. Okay, so this is very straightforward calculation, but it really, if you repeat this calculation for a variety of approximation, it does quite magical things. So that's basically what we have summarized in the paper, is that you choose posterior approximation and you choose then some algorithmic approximations. Like I showed you gradient descent, you derive it by doing Gaussian with fixed covariance, then you do delta approximation. Then if you increase the complexity of the approximation, so you go to Gaussian with a variable covariance, then you recover Newton's method. And if you go to mixture of Gaussian, then you go to different local minima in the same run. So you cover the space more. You could do the same thing with deep learning algorithms. So do mixture of Gaussian with 2 mixtures, you get dropout. Do Gaussian, you get SGD and RMS prop and atom and other things. And also many Bayesian algorithms you can write with that. So of course, many things in conjugate Bayesian world, Laplace's method, EM algorithm, stochastic variational inference, variational message passing, and all sorts of other things that people have actually worked on. So all of this with one single rule. And there's no magic here. It's actually basically you choose the approximation, and the approximation has certain moments, certain sufficient statistics that you need to estimate. And those sufficient statistics just fall into the right place to be estimating the right kind of gradients or messages in message passing. And that's basically what happens. Okay? So it's summarized part of it in this paper. The paper's almost done. I've been saying that for almost a year now. But we're now writing the discussion section and doing some notations, simplifying, but it should be out in some time. What we actually did with this work in last few years is that we try to take traditional deep learning algorithm, so like they make these kind of approximation here. We relax these approximations. So we say, well, we're not going to do this Hessian approximation that's done here, but we're going to do a Gauss-Newton approximation. Or we're not going to do square root because it messes up with the variance estimates. So we did this modification and we got new algorithms. So this is online Gauss-Newton and variational online Gauss-Newton method. And with that, we can get better estimates of uncertainty without changing the code much. Okay, so I showed you this example before. Basically, it's this algorithm, variational online Gauss-Newton method. which is just a simple modification over atom. And uh, so it performs quite similarly. And on ImageNet, it gives like almost same convergence rates, matches the performance of atom, but in addition, it gives us the estimate of the covariance, or of the variance. So it gives us uncertainty. So it's on this 2D example, you can see the samples that are drawn from this method. You can get the code in this web page and check out these two papers that we have written on it. And these are basically derived from our original paper that we wrote in 2017. You can apply this to more realistic problems, like on this computer vision problem, and it works quite reasonably, as you can see here. So these things are summarized in this paper. This paper is actually basically just giving a big picture overview, a review of everything that we have done in the last few years. And this idea actually came up with when I was talking to Howard Drew, who occasionally visits us in Japan. And we are now summarizing these things in this paper. This paper is actually, I would also encourage you to check out another paper of a similar style by Jan Olivier and some other people. And this is kind of written for information geometric optimization. So this paper is showing that many optimization algorithms can be sort of written in the same way by using this information geometry, which is a natural gradient descent. And this paper that we are writing is really a similar paper, but now, and we are using information geometric optimization, so it's just natural gradient. But here, everything is motivated from Bayesian principle, meaning that the distributions that we are trying to estimate are approximation to the Bayesian posterior. So that's the tweak here, and this is actually helping us to connect even more algorithms like those that exist in deep learning, in continuous optimization, and also in Bayesian inference and the classical Bayesian inference. Okay, so also check out this paper. This is also a very nice paper of similar style. If you're interested in knowing more about this, and here I really went very quickly over the details, so you can see my NeurIPS tutorial, which was specifically focusing on deep learning applications of this. And it was quite popular for a while. So it was like the third most watched talk at that time. I don't know what's happening right now, and I think Slide doesn't keep track of the views. It's not that important, but I will encourage you to look at it. It's a good summary of what I'm talking about here. Okay, a little bit more about what has happened around this line of work. So all of this natural gradient stuff, as I said, started so this was work with Wu Lin, who was a member at that time in our group. And we wrote this paper, and this was kind of a narrow paper only focusing on variational inference and Bayesian inference. And Wu then extended it to mixture of exponential family. Connection to natural gradient is also written here with Didrik Nielsen, who was also a team member at the time. And now he's in Amsterdam as a PhD student. Wu has extended this to mixture of exponential family. It's a very nice paper where we show that the same kind of message appears when you go to scale mixture of Gaussians or finite mixture of Gaussians, like T distributions and like low rank approximation. Wu has been working on this during his PhD now, so he has actually written a new paper that's it's on arXiv. You can check that out. It's with Frank Nielsen, and Mark Schmidt is Wu's PhD supervisor. So he has written basically on how to generalize all of these things that we've been writing before. And it's very beautiful that in the end, what you see is that the basic message is not changed. So So for example, if you use Gaussian approximation, you use covariances of like, low rank or diagonal or structured, some Kronecker factored approximation. No matter what you do, you in the end get something that looks like Newton's method. So he has many of this sort of example on like other kind of approximation. Just very nice work. I encourage you to check it out. These things that I was showing before, they were all really just on the Gaussian approximation. So it's done with a bunch of people here, and I'm running out of time, so I'm gonna just quickly go through this. We've also done work on binary neural networks. So this is like using Bernoulli approximation, and some recent work with Gaussian processes. And I think in the Gaussian process world, people have really ignored natural gradients, have not used it as a mainstream algorithm, but this algorithm is quite beautiful. It's sort of a generalization of what James Hensman has actually done. This paper is quite well cited. Okay, so this was done with a couple of interns and postdoc and collaborators in Aalto University. And with that, I will stop. So far, I've talked about learning algorithms from Bayesian Principle. Now we'll move on to our current work, which is about knowledge representation and its transfer. So I'm going to hand it over to Dharmesh, who's going to talk about memorable experiences. Basically, what he's going to show is this kind of simple example where you have these data points and you draw a line in between. So that's classifier. And you think about like, I ask you a question like, which is an important, better classifier. And now he's asking a question of like, which is an important data point. So it's more about examples than the model. And essentially, it turns out that the Bayesian principle sort of give you these two views of data view and model view. And from the Bayesian principle that I just showed you, you can sort of derive the importance of the data. So this is what Dharmesh is going to talk now. And so I'll give it to Dharmesh.
Great, thanks, MT. So here I'm talking about identifying memorable experiences of learning machines. My name is Dharmesh Taylor, and this is joint work with Paul Chang, Arne Solin, Staff Swaroop, and MTS Khan. So humans have this notion of memorable experiences, and how can we do the same in machines? We show in this work that memorable experiences of a wide variety of machine learning models can identify with a single Bayesian principle. To illustrate this, we show here an example from regression where the red dots indicate data points, and we seek to draw some line through the data, say by ridge regression. Here the regressive fit is indicated by the black line, and we show predictive uncertainty by the gray error bars. And memorable experiences for this model could be as follows. We can do the same for more complex models, such as Gaussian processes. Here the fit is much better, and memorable experiences for this model and data could be as shown. And also for neural networks, we can do something very similar. There's similar fit for the data, and a different set of memorable experiences are these ones. We will show in the coming slides that there are different criterions for memorable experiences. But before that, let us consider another example from classification. So here I show a classification example. This is the MOONS data set. It's a binary task to separate between the blue squares and the red circles. We can consider drawing a logic regression fit, and the decision boundary is shown by a solid black line, and memorable experiences in this case could correspond to those along the decision boundary. We can again, in a similar fashion to for regression, consider more complex settings, for instance, Gaussian processes and neural networks. As we can see here, if you compare GPs and neural networks, they have similar predictive performance, but the memorable experiences are quite different. And so we want to emphasize the point that memorable experiences are also a model-specific matter and not just a matter about the data set in question. Before we go into the details of our work, I want to just mention some related work that this is based off. So one topic that is quite classic is the idea of influence from robust statistics. This considers the effect of removing data from the training set, retraining the model, and looking at the change in the model as a measure of the influence. In some settings, for instance, in regression, such change can be quantified in closed form, and this gives rise to such regression diagnostics, which includes the residual, leverage score, and their combinations, for instance, Cook's distance. In nonlinear settings and beyond regression, they can overcome this by considering influence functions that construct a local approximation of the objective about your minima. And this is recently introduced into machine learning by this paper by Ko and Liang in ICML 2017. You can also see sparse Gaussian processes as an instance of what we'll be showing. So in sparse GPs, this overcomes the intractability of doing exact inference, which is scales cubically number of data points, and they do this by constructing a reduced size matrix. Those columns or inducing inputs are typically learned automatically in a variational Bayes way, but previously many approaches that use the data points themselves as inducing inputs have been proposed, for instance, incorporating them into an active set in an online fashion using various acquisition functions, as mentioned in this paper here. More recently, they proposed selecting the columns by sampling from the ridge leverage score, and that was shown in this paper by Bert et al. And our work is very similar to this. Support vectors, of course, support vectors are a sparse representation of the data sets. That's a consequence in this case of the particular loss used in support vector machines that gives rise to sparsity, and the resulting predictor is sparse. And as we will show later on, in the case of support vector machines, the dual Lagrangian is the formulation used to optimize SVMs, and we'll show that what we consider also optimizes in a dual Lagrangian way, where we kind of optimize an n-dimensional vector of joules. And core sets, of course, consider a kind of small weighted subset of the data. And many approaches have been proposed here. One such approach recently proposed was dim bi-level optimization. And yes, memorable experiences unify and generalize all these concepts by starting from a single Bayesian viewpoint. So we show here the case of ridge regression, which optimizes this objective. We have squared error between targets and linear predictor. This is our loss, and we have an L2 norm on the regularizer. So by Lagrangian duality and event of the representative theorem, the solution of this objective, W star, can be related to an n-dimensional vector of joules alpha, and this relation is via the design matrix X, which is all the covariates stacked. This can be understood as moving from the model view to the data view. And of course, for ridge regression, W star is a closed form solution, and so alpha does as well. But alpha can be reformulated as the residual, so the difference between the targets and the predictions on the data. This is one such way we characterize memorable experiences, and this can be shown to be equivalent if we consider a component of alpha to be the gradient of a loss, and we will revisit this and encounter this expression as we go to more complex settings like Gaussian processes and neural networks. Before that, another way to view the data space is that of ridge leverage scores. Ridge leverage scores are the diagonal of this matrix H, which is called the hat matrix, that projects the observations to the predictions on the training sets. They're related to the complexity of the model and measures the number of dimensions of the model, and they're quite commonly used in those ways. But the expression for this in kernel views as follows. Here we show that the kernel corresponds to a dot product kernel of the covariates. This is commonly used, for instance, in this recent work to obtain a reduced size regression problem by sampling from the ridge leverage scores. And it's recently been extended to sparse GPs as well, as I mentioned. And we consider ridge leverage scores as one such characterization of memorable experiences. Here we show some examples now. So this is revisiting the examples we showed on the second slide. And this shows for ridge regression. This is a residual where the memorable experiences are those furthest from the regressor fit. In the case of classification, we can do the same for logic regression. The previous relation between W star and alpha star also holds. And in this case, it identifies points that have been misclassified. This is consistent with support vectors, where support vectors are not only points which are on the margin of the of the support vector machine, but also within on the other side of the margin. And we show here a example for leverage score for ridge regression, which identifies points at the boundary of the data. We now go to Gaussian processes and we consider optimizing a variational objective if we consider our likelihood to be non-Gaussian. We seek to find a Gaussian posterior approximation, Q, parameterized by moments M and V. We have a zero mean prior with gram K. We consider the fixed point of this objective, which recovers a similar expression to what we saw for ridge regression, with this relation between the model view and the data view. And here the mapping is now done by the gram K. And we recover a similar expression for alpha, which is the gradient of a loss. I've defined the loss to be log likelihood. And there's an expectation in front, which comes from the expectation in the variational objective. We also have a second expression resulting from a fixed point with respect to the second moment parameter, V. In this case, we see V is related to another n-dimensional vector of joules, which we label as lambda. And lambda is equivalent to the second derivative of the loss. So closely related to the covariance is the leverage score, in which here we replace the usual ridge term in the leverage score with lambda. This is motivated if we consider this paper here, which gave the interpretation of alpha and lambda as a solution of a dual problem for variational inference, where lambda in particular corresponds to a constraint on the variance, a similar curvature constraint as one can interpret of the ridge term if you consider a QP formulation of ridge regression. We now consider some visualizations of these criterions for Gaussian processes, here for residual. And we see these are points that are furthest from the boundary. And for leverage score, we show, so here now the fit has improved. And so we have this in-between uncertainty showing, and memorable experiences are those at the different boundaries of the different clusters of data. And leverage score can also be shown for classification, where we see points being identified at the boundary of the data and in the usual ridge leverage score way, but also close to the boundary as indicated by these points. We can move towards neural networks by considering the usual neural network loss within the Bayesian learning problem that MT outlined in the previous talk. We have a loss function of an L2 norm and the entropy term that MT stated. And here we select a Gaussian family to be the family to optimize. And in a similar fashion to a GPs, we consider the fixed point or solution of this Bayesian learning problem. And we recover similar fixed point expressions to that of GPs, where we have now a Jacobian matrix replacing the gram. We can equivalently define a leverage score, which is closely related to the covariance. So in this previous work from our group, we gave a GP interpretation of neural networks, which showed that the prior of doing approximate inference in neural networks corresponds to neural tangent kernels. You can see here, this would be the gram that corresponds to the Jacobian transpose. And we also have lambda appearing here. And this paper gives another interpretation of lambda as being the input dependent noise term of an approximate linear model. And we show some visualizations of these criterions for neural networks. And so we see very similar to the case of Gaussian process regression. Memorable experience are those furthest from the decision boundary for residual and at the boundary of the data in the case of leverage score. And here we show for lambda, which identifies points close to the boundary, as we can see. So I mentioned various criterions for characterizing memorable experiences. Now a very valid question arises as to which criterion should be used, and this depends on the application that one has in mind. So if we consider, say, lifelong learning with no task boundaries, you may want to identify points at the boundary of the data space, in which case, as I hope I've sort of shown in the plot, the leverage score would give you this. In contrast, if you are doing a kind of offline setting where you want to identify examples for further inspection, say if they were potentially mislabeled or adversarial, then the residual could be the criterion to use to identify such points. In some previous work, we considered continual learning with task boundaries, where a sequence of binary classification tasks were learnt, and we want to here maintain the decision boundary as we move across tasks. And so lambda would be a sensible metric to use here as it identifies points at the boundary. To emphasize this, let us visualize some of these data examples. In the case of MNIST, we show examples which have a large value of lambda. And so these are quite atypical of their class. They're irregularly shaped digits. And to compare this, we can show ones with a small value of lambda, so least memorable points we call these, which are quite characteristic of the class, quite typical in their form. And the same can be shown for the CFAR data sets, and I'll show here most memorable and least memorable. And hopefully the difference here is quite evident. We see that most memorable examples have their objects in different positions, poses, sizes. In some cases, they're occluded, and it can be hard to identify the object from the background. In contrast, for least memorable, the background are usually quite light colored. They are center pose in the sort of pixel frame, and one could say that these are what humans would find easy to classify or difficult to classify as well. So here we demonstrate that memorable examples are the most impactful to model performance. We show this by removing examples from the data sets, then retraining the model from scratch and evaluating the model on a unchanged fixed test set. We do the removal initially by just picking points at random, and this is shown by this purple curve here. We compare this against training a model on the full data sets. We then evaluate one criteria. In this case, it is extension of the leverage score, and we order examples from most to least memorable and remove examples in that order and report its test set performance. And we see a considerable deterioration if you compare against a random baseline of the test set performance, showing that memorable examples are indeed the most impactful to model performance. So I've shown in this talk that memorable experiences of a wide variety of machine learning models can be identified with a single Bayesian principle. I have indicated a number of different criterions, and their use depends upon the application one has in mind. And I demonstrated that memorable experiences are the most impactful to model performance if they are removed. This work should be out soon, so please keep a lookout for that, and thanks for listening.
All right. Thank you. I'm sure everybody's clapping very hard and we just can't see them. Well, we should maybe stop for some questions. And actually, Dharmesh, you saved a lot of time for us, so you went quite quickly. So that's great. Okay, so I will read some questions. So there are two questions so far. And the first one is by Chibin. And he is asking for my talk, when we apply Bayes' algorithm to deep learning, how is the assumption on Q of theta, so the distribution, and do we learn joint posterior for all parameters from different layers, or simply independent assumptions for them? In addition, how to choose the form of Q in practice? And this is a great question. So for deep learning, mostly what we see is that if you choose a Gaussian form, then it's enough. And most of the time, it's Gaussian are just like mixture of Gaussian with two components, which is used to get dropout, for example. And of course you would want so you do this for all parameters, so parameters over all layers, and you might want to do full covariance over the parameters, but then that is quite computationally expensive. But luckily, if you assume them to be independent of each other, then you recover Adam. So Adam is using the scale vector that is just a diagonal scale vector, and that scale vector turns out to be the inverse of the covariance, which is also diagonal in this case. So If you do diagonal Gaussian, then most of the adaptive learning rate algorithms that people use are kind of like I shouldn't say recovered, but you can get an adaptive learning algorithm form by choosing Gaussian with a diagonal covariance. Um, the last part of the question was how to choose the form of Q in practice, and that is that is the point of all of this. So basically, well, of course, what Bayesian says that Q should be as close as possible to the true posterior. But what we kind of see now is that if you want to match the performance of existing non-Bayesian methods, you actually don't need it to be so accurate. So if you choose to be Gaussian with diagonal covariance, you still can match the performance. So the point here is that it should be slightly more complicated than that, depending on what kind of uncertainties and what kind of gaps in the data that you're looking for. And you essentially, when you're doing exploration, you want to identify the boundary of the knowledge. So this is why we're getting into these ideas like what Dharmesh is just talking about, memorable experiences. So like trying to dig out these points or the edges where the data tells us that the knowledge is uh, till this part is known and we don't know beyond that. And this you could do with very simple distributions. So far it seems to be okay with just Gaussian and some variance built on top of it. And I think computationally we don't want to go too complicated more than that. So we'll see how this will work out. Okay, so that's hopefully that answers the question. But there's a second talk. Second question. So, what is your opinion about Bayesian algorithms for adversarial samples? Due to the maximum of the entropy, is it naturally more robust to adversarial samples? So, yeah, I mean, I would expect it to be that way, but the entropy is not really it's not thinking about the adversarial settings, right? Entropy is there for letting you do more diversity, but it's not written to solve the adversarial learning problem. So here we do expect that it will be more robust because diversity makes you more robust, but for it to be robust to adversarial samples, I think you need additional mechanisms to be put in place. But I think this is like a classical thing between max min kind of framework versus the Bayesian objective here. I think Pierre could probably answer this better, but I will leave that answer here. Okay. Um, if there are no questions right now, we can move on with the third part of the talk. So, okay. So thanks a lot, Dharmesh, for your talk. Uh, I will. So if you have more question about my talk or Dharmesh's talk, please continue to write them in the Q&A, and we'll be happy to answer them after everything ends. All right. So far, what we have talked about is the Bayesian principle, deriving learning algorithms from Bayesian principle, and then representation of knowledge using the same Bayesian principle, which is called memorable experiences. Now I'm going to show an application of this. So this will be a very short 15-minute segment on continual learning. And this is the work done with many wonderful people. So Pingbo and Siddharth are the first author of this work. And Runa is an intern from University of Osnabrück, and now he's a student in Max Planck, and Rich Turner, who is supervisor of Siddharth. And this is kind of based on this Gaussian process point of view, which Dharmesh also talked very briefly about. And that was done by Alex and Ehsan and Maciek, who were also interns in the team in 2019. Okay. So this part of the talk is about knowledge transfer. And basically, we are considering this different type of learning, continual learning, which is different from standard deep learning, where you assume that all of the data is present at one place. So you have like huge ImageNet data set, and now you have the freedom to go and randomly sample any image that you want from there. Now, in continual learning, you restrict this setting and you say, now I'm going to make it a little bit more real, where it's some sort of sequential learning where there's some restrictions. So one popular restriction is that the classes are coming sequentially. So you're not free to sample classes arbitrarily from the data, but you observe them. So at this time, you may observe only dog versus cat, and you have to update the network, and then you will never observe these, and then you will observe lion versus tiger, and you don't have access to the past classes. Okay, now you want to do this kind of training because this is a little bit more realistic setting, and the standard training already, if you run like stochastic gradient descent, where you sample mini batches from your current data, it turns out that the network starts to forget the things that happened in the past, right? Which would make sense because it's not really a unbiased stochastic gradient anymore. Okay? So this problem of continual learning is like, how do we fix this catastrophic forgetting? At least that's one aspect of that. And there's a lot of work that's been done in this, and this all kind of restarted the work on continual learning. Is this paper from DeepMind on catastrophic forgetting, and they actually used Laplace approximation, which is an approximate inference method from the Bayesian literature. And some people have actually built variants of this, so with structured Laplace, something called synaptic intelligence, and doing a variational inference version of this. But then there are alternate, ways to do by using memory. So storing certain data points from the past so that you don't forget them. And then some work where they have tried to measure the discrepancy between the network output over these locations that you have stored. Now, all of these methods are in good spirit, and they do work to some extent, but they're not enough. So this slide is sort of giving you an idea of where we are in terms of performance. So this is on CFAR 100. And what we have done is we have made 6 classes here. So we have split 10 classes each, and some classes to kind of warm start the learning. And what I'm showing you here is accuracy in the y-axis, and the black line shows the best possible. So like if you didn't do continual learning and you had all the data at once, then you will get this performance here. Okay, so our goal is to actually get to this black line, but you can see that most of the methods, there is a gap between the thing. What I've shown here is this Vaughan. This is the Bayesian learning rule that I showed you before in the animation, this variational online Gauss-Newton method. That performs quite well, but still there is a room for improvement. Right? And methods like the pure Bayesian methods, which is this variational inference method, they actually perform really, really poorly. So the gap when you do these Bayesian principles and you use this atom-like learning, you get a huge improvement. So that's the good news. But still, these things are not really matching the thing. So they're still using these kind of Gaussian approximation in deep learning. Straightforward application of Bayesian principle does not really solve the problem. So this talk now is about how do we improve the results further. And the main idea is basically based on what Dharmesh was talking about, right? So I showed you this figure in the beginning that, well, you have to pick a line, and you can't really pick it properly because it depends on what you're going to see in the future. And here you were thinking in terms of lines, right? But what we are now saying is that, well, there's an alternate way of thinking about it. So it's about knowledge representation. So when you had observed this first set of data, instead of thinking about which line is fitting it better, why not think about the alternate view, which is the data view. So it's the model view is trying to draw the line, but the data view is trying to think about which data points are the most crucial to make sure that the data is classified well. So this is kind of these boundary points, and Dharmesh called it a memorable experience. And this term actually comes from this paper that we wrote in 2020. So that's the paper that I'm kind of summarizing. So the basic idea is that you, instead of thinking about these lines, you're thinking about the memorable examples, so the data examples that are important on this previous data set that you observed, and you identify it using the Bayesian principle that Dharmesh talked about. So you look into the derivative of the loss and the second derivative of the loss, and then you pick some of those examples. And then when you observe the next set of points, you say, I'm going to try to fit this next set of points, but such that I don't lose the performance on just these points. Okay. So that's the kind of the idea. So there's two steps. You identify a memorable example and you regularize the network output. I'll give the more details soon, but we call this functional regularization of memorable past, FROMP. And basically, it's just a simple modification of Adam, because you're adding few points from the past and then you're regularizing at them. And visually, the way it actually works is that you get the first set of data. So this is task one. You fit a model. Then you identify a memorable example here. So these are the similar ones that Dharmesh was showing. And then when you get the next set of data, you try to fit a line that goes through this data, but also through the past data. Okay. So this is the regularization part, that you fit this data while regularizing the network output at this place. So you continue like that. You identify a memorable example again, and then you go to the next set of tasks, and you try to make sure that the past is not forgotten. Okay, then you continue. So a little bit of mathematics of how, I mean, Dharmesh actually gave you some idea of this, but this is really like based on um, this same Bayesian principle that I talked about in the beginning, that you're using this kind of thing. And basically, you can use this the gradients that you compute here to pick the memorable example and then regularize them using those. Okay, so I just wanted to give a little bit more detail, and it's basically kind of an extension of what Dharmesh was talking about. Just notice that this algorithm converges. So it doesn't have to be just this, but this makes it easier to just look at the convergence point of this algorithm. So when this algorithm converges, basically, because the gradient of the entropy is just lambda, at convergence, you get like the gradient of this is equal to gradient of this. Okay, so that's what I've written here. So lambda is the gradient of the entropy, which is the natural parameter, is equal to the natural gradient. Now, this is a fantastic point, and it's kind of often missed in the current literature in variational inference, that whenever you're doing variational inference, like it's not just natural gradient variational inference, but whenever you have a Bayesian objective, always the solution is of this form, that natural gradient is at the right hand side and natural parameters on the left hand side. And this is for exponential family approximation, but this sort of relationship holds in general. Now, this Bayesian learning rule is actually just kind of, this is a fixed point of that Bayesian learning rule. And you can use this relationship to identify examples and then find a mechanism to regularize them. Okay. Basically, like if you start to write the natural parameter, like the mean, then this gradient just splits into the gradient of the individual data example. And then this you get like, this is like Jacobian times the residual. So this is the relationship that Dharmesh was showing. Same thing if you take the covariance, this is the precision inverse of the covariance, then it's related to the second derivative plus some regularizer that you can write or approximate with the Gauss-Newton approximation. So you get these lambdas. And essentially, this is the dual variable that Ramesh was talking about, of how you use them then to, these are the ones that are lying at the boundary of the classifier. So not only that you can extract this information at the minimum, but you can actually always extract it from this Bayesian learning rule, right? So you can see that this natural gradient here is essentially containing the information about alpha and lambda. So you can always extract them from the iteration or at the solution, and then you can use them to do something else. So to do knowledge transfer, right? And basically, this work is so the details of all this is in this paper that we call DNN to GP. This is written in 2019, um, and it's kind of like an old work that I did back in 2013. Sort of talks about the duality of all of this, and that was limited to convex problems. But the thing that Dharmesh really talked about on like how to do the same thing for Gaussian process, for support vector machine, for kernel ridge regression, or neural network, all of this kind of based on this type of duality, where the dual variable alpha and lambda can simply be extracted from these natural gradients. So I know that there's a lot of details here, and it takes a little bit of time to absorb that, but the references are right here if you want to check them out. Now, let me again show this a little bit more in an intuitive fashion. So what we actually, I showed you this thing before, that you want to make sure that you don't forget the past and you make the right choice. The weight regularization methods are working in the line space. So they're like kind of saying that the line should be closer. So the new parameter should be close to the old parameter, and some weighing to make sure which parameter is more important. But thinking about parameter is not the right thing, because parameters don't really matter for neural network. So this functional regularization idea that I just showed you is trying to do this instead of in this parameter space, it does it in the function space, right? So in the data space. So you replace the KL between PQ. So this is like KL between PQ in the weight space. And then you replace it by KL between PQ in the function space. So F is the function defined at these locations. And if you write down the KL, it basically comes out to be making sure. So XM is the memorable examples, and F by the new model at this point should be similar to the F, the function at the old model. And then you put some weight to make sure which data point is more important. So this actually just pops out from the Bayesian principle, and the detail of this is written in that DNN to GP paper. So very surprising result is that turns out that this kind of regularizer form, not exactly this, but this type of form is actually optimal, meaning that if you wanted to get this red line that's obtained by maybe training on all of the data, like joint training on everything, you can recover that if you are able to choose these points properly. Of course, choosing the points properly is a difficult task, but if you could do it, then this form will get you to the exact solution. This is a very strong result, and it should be out soon. So keep an eye for that. Okay, so just wanted to end by showing you some results. So it's the same graph as before, but now I've added fromp in here, this functional regularization method, and you see that fromp is sort of bumping up everywhere. So this purple line is kind of improving the performance at every place. Of course, it's not performing as well as we would want it to, so it should be here. But there are these practical choices of like how much computation you have and how efficiently you can actually identify the past given the present, and there are these trade-offs, and you cannot make a perfect choice always. But we are now kind of working on improving these results further with the new theory of optimality that we have. Okay, this also on, this is the comparison where the method from DeepMind people is also added, where, so this method, this functional regularization, this from DeepMind, and this is not performing as well as what our method does. And we believe that it is because of this reason that we are able to select the memorable example better and regularize them in a better way. Okay, so with that, I will stop here, and not sure how many questions we have, but I basically, I will come back to the slide after Pierre is done to close the talk, uh, but I will hand it over to Pierre. But let me look at the questions. So there's no questions right now. So, okay, so Pierre, you're up.
Here I am. Okay, so thank you, MT, and hello everyone. So I'm Pierre Alquier from the ABI team in Recon AIP, and I'm going to talk now about meta learning, and the objective being to learn tuning parameters, or also called hyperparameters, with guarantees. This is based on a joint paper with Dimitri Meunier. So just a word about Dimitri, actually, who applied actually for an internship at Recon AIP last year. And obviously, like as all the students who applied for internships, not only in Recon AIP, but all over the world, the internship had to be canceled, and obviously for good reasons, but even though it's for good reasons, I still feel a little sad for this generation of students who could not enjoy these experiences that we all could enjoy in the past. And I also want to say thank you to all the students who applied for our team, because actually all of them decided, even though they were not officially coming to Recon IIP, to work remotely with the team for a few months. And that was the case with Dimitri, actually. So even though he was not officially part of Recon IIP, he worked with the team by attending the reading group every week, and in the end, this led to the publication, at least to the submission, sorry, of this paper. Dimitri is now officially a research assistant in IIT in Italy. But then, like, as I said, this work was mostly done within the framework of the team. So this paper is about meta-learning. I will try to motivate it just through a learning example. So very simple learning problem. You have some data, and the data is represented here, sorry, by this array of numbers here. So very simple numerical data, not structured data. And the data is sent to a computer, or maybe to a big server if it's like huge data. And you expect an output. I did not specify what kind of output, because the output can be a data analysis, it can be a parameter with a confidence interval. In this setting, I would be more interested in predictions, but actually the framework I'm going to present can be adapted to many kind of outputs. And the point is that apart from very simple case where we decide to use maximum likelihood estimator, for example, but in general, actually, the algorithm that we have depend on extra tuning parameters or hyperparameters that are not so easy to calibrate. So this is why here I drew, like on the left of this data computer and output flow, a person who is a statistician or data scientist, and this person on his or her laptop has to tune these little buttons to decide the value of these hyperparameters. And just to make things less abstract, more concrete, a very simple example, assume that you have small data sets that you want to use for high dimensional regression, and you want to use the lasso estimator. Then you have this gamma thing, the constant in front of the L1 penalty to calibrate. Or assume you want to do ridge regression, same, you have a constant in front of the penalty. And actually here I represented a linear model, but it could be as well a more complex model like a neural network, and you still have a penalty, and you still have a constant in front of the penalty. Okay, so the question is how to choose this. And it appears that even though theory, like for the lasso, you have a theory that tells you that the estimator will be consistent and maybe optimal on the condition that gamma is of a prescribed order of magnitude. But who says order of magnitude? Say that there is a constant to tune in front of this order of magnitude. And here again, we don't know what it is. So actually, I'm going to plug this problem in a meta-learning context. What does it mean? It means that actually, instead of considering just the analysis of one data set, well, I will consider the analysis of many data sets sequentially. And the idea is as follows. If I don't know how to tune this hyperparameter from the beginning, maybe I could learn it through time. So I could, on the data, acquire some experience and remember this experience so that for the next data set, I will have a better idea of how to tune them. Okay? So you just see that in this case, you have a data set and your computer is going to produce some output and you expect that it's good and that it's useful for whatever you want to do with it. But still you can here remember some information that you can reuse on this computer or another one when you have to analyze the next data set and to produce here again an output. And you can hope that if you solve many tasks, many learning tasks successively, then at some point you will have a good idea of what the optimal hyperparameter is. Of course, there's just one thing. You know that for the lasso, for example, the hyperparameter does depend, of course, of the data set. It's not always the same. Otherwise, it's like we could just learn it once and for all. It will depend on the data set. And the idea here in this meta-learning problem is that what I will present now will work essentially if there is some similarity between the data sets. So it does not mean that all the data sets have to come from the same distribution, but you can assume that, for example, it's biological data set that would come from the same set of exams or physical data set with data acquired with the same sensors. And so actually that the data is on the same scale and that they share some similarity that makes you believe that actually the same hyperparameter could be used with all the data sets. Okay, so I'm going to use a meta strategy, and by meta strategy, by the way, I don't mean anything magical. I just mean actually a learning strategy, but each learning, each point in the sense of this learning problem will be a full data set, a full learning task. Okay, so the idea. Here I will just present a kind of very abstract framework, not very formalized, and I will make things slightly more formal in the next slides. But the idea is that I will propose to you a meta strategy that will work as soon as actually here the computer, within the computer, what is running is an algorithm for which you already know a generalization error bound. So if the algorithm within the computer has a generalization error bound, that depends, of course, on the current data set and on the current value of the hyperparameter you use, then let us denote by LT of lambda. So the generalization bound on the dataset T and using hyperparameter lambda. And actually, I just propose the simplest thing to do in this context, that is to use the already existing online optimization theory to minimize the sequence and the sum of the LTs. So actually, we use very well-known strategies known as the online proximal strategy, or follow the regularized leader, but it's a version of follow the regularized leader. But as I use it at the meta level, I just propose to change the name so that it's clear and to call that online proximal meta strategy. And the idea is just that at task T, you use parameter lambda T, and then you solve the task. But then at the end of the task, if you want to know what parameter you will use, what hyperparameter you will use for the following task, you actually minimize this problem. So you minimize the loss, the error bound at task T with parameter lambda, plus a deviation term, lambda minus lambda T squared, which will impose some regularity in the sense that if there is some difference between the data set, you don't want that the lambda T oscillates very strongly. Actually, you want to stabilize it to hope to have some convergence in the end. Okay, so it might sound a bit abstract when presented under this form, but I will provide an example. And in order to provide an example, I will just specify what are the kind of data sets that you have, what are the algorithm running within the computers, and what are the kind of output expected here. And then I will show you how to use this meta strategy. Okay, so I will focus, and this is an arbitrary choice, and we can focus on other contexts. But in this talk, I will focus on tasks that are online prediction. Actually, it could be online regression tasks. Okay, so each task starts with an object that will be given to you, and then actually you, with an initial guess for a parameter, you try to theta t1. You try to predict the label corresponding to this object. and then you observe the true label. And then given this observation, you try to update and to improve your initial guess on the parameter. And then the second object comes and you try to predict using the Brilliant predictor taken at theta t2, your new guess, the label of xt2, and then actually the true label, yt2, is revealed, and then you update, and so on and so on. Okay, so actually, how do we do the update? I will talk about that in the next slide. But first, you have to quantify, of course, what would be a good prediction. So when your guess of yt1 is a good prediction of yt1. So in order to do this, I will use a loss function, L. And just for short, I will use LTI of theta, so that the loss for task t and observation number I of the parameter theta, and it's just this, the loss between yti and f theta of xti. So think of the absolute loss or the squared loss, for example, or logistic loss if you're dealing with 0, 1 labels, etc. So this notation, sorry, nothing to worry about. It's just to make things short, because I don't think that there is a need to write xty and yty in all the formulas that will come later, and some of them are a little bit cumbersome. Sorry about that. So the objective here is to learn live, is to learn as soon as the data come to be able to predict the next one. Okay, so it means that I want a strategy so that the sum of the LTI of theta ti, okay, will remain as small as possible. And now I will present you a strategy that is popular, first because it is, even though it's not like the one that is exactly used in many problems in practice, but that is the basic idea beyond most methods. And also because, of course, it's quite simple, and so it's in every textbook, is the online gradient algorithm. And the online gradient algorithm, so that's actually the way we update from theta t1 to theta t2, theta t2 to theta t3, etc. And the formula is simply given by theta ti plus 1 is theta ti minus eta times the gradient of the loss LTI at theta ti. Okay, this is well known, and if you learn about online optimization or online learning, then actually, usually this is the first strategy that is studied. So in any textbook about online optimization, you will find the following so-called regret bound for the online gradient algorithm. So each LTI is convex. If each LTI is convex and Lipschitz, then actually this quantity that we want to minimize, that is the sum of the live predictions. So the sum of the prediction that you make on example TI based on the past information, but not on the knowledge of this example, of course. Then actually it has a generalization bound, and this bound is given by the infimum for theta on a ball centered around 0. So the infimum, the minimum of the possible sum of the losses of LTI of theta, which means that actually you perform as well as the best theta on a given set, had you known it in advance, which you did not actually. But of course, in order for this bond to hold, there is a reminder that is the price to pay for learning. And here you see that this reminder, as you would expect, it depends on two things. It depends first on eta here, and it depends also on theta 1t. What is theta 1t? Well, remember the beginning of the story here. Theta 1t is your initial guess for the parameter. And actually in the online gradient algorithm, well, it's given by your recursion formula. So it has to have a starting point, an initialization. So actually, the regret bound depends on two things. First, the initialization, and then the gradient step. So it's exactly the framework I described before. We have a method. This method has a bound that you can find in any textbook. And this bound depends on the hyperparameters, eta and theta 1, that actually you don't really know how to calibrate in practice. So let me call lambda, as I did before in the abstract setting, the pair, eta, theta t1. And this quantity here, this upper bound, will be LT of lambda, as before. Okay. By the way, I just want to take the opportunity here to answer to Kubin Sao's question. In this case, actually, we don't have to assume that the data xty and yty are IID. So this bound is valid even in the adversarial setting, actually. Thanks to the regularization, and it will be true later when we will replace this regularization by an entropy. So just one thing about this bound, because maybe it's not clear how tight it is. You see that here, even though you don't really know how to tune eta in practice, there is an n here, that is the sample size of the task that appears in this term. And if you consider that everything else is more or less constant, then actually you see that you have to take eta in 1 over square root of n. And then you obtain that actually the sum of the losses is the best possible one, as small as the best possible one, plus a reminder that of the order square root of n. And you might say square root of n is big, but remember that you have sums here that are compared. So maybe if you think in statistical terms instead, and you compare means. So this is the mean prediction error during the task, and this is the best possible mean prediction error. And then you see that the difference between both is upper bounded by 1 over square root of n. So actually, this is something that as soon as n is not too small, will be reasonable. Okay, so that's not our work. By the way, that's just like the basic online gradient strategy. And that is what will be used to solve each of the individual tasks. Okay, so I will summarize. Sorry, like there's maybe notations maybe on this slide, but on the top here you see like the very basic drawing I presented before with the different data sets, and for each data set you have a computer that will use it to produce some output. Here it is the online predictions, but then when the task is complete, you want to send some information to the computer that will solve the following task. And here actually, so we will produce the sequences of the theta t1, theta t2, theta t3 of the parameters. But then when we reach the end of the task, we will start with a new data set, but instead of throwing away all the information, we will pass to the next algorithm the information on lambda. On lambda, remember, that is the pair gradient step, eta, and initialization, theta t1. That's what we are going to do. And now I presented before a very abstract meta learning strategy, which was how to update the lambda, the hyperparameter. Now I will, I will remind you what it is, and now I will use it in practice on this example. And the definition, like I just applied the definition. So actually, the new, given the previous hyperparameters, eta t and theta t1, then the new one, eta t plus 1 and theta t plus 1, will be learned by minimizing the sum of first the regret bound that we had before, so the optimal set of the losses, plus the reminder that depends on a possible initialization, theta red, and a possible gradient step, eta. But eta is constrained not to be too far from eta t, and red theta is constrained not to be too far from theta t. So you just solve this at the end of each task, okay? And if you solve this, then actually you are using our meta strategy. Now, I will try to provide a theoretical result on this. And the question is, of course, when you see like an inequality proving that an algorithm reaches such or such level, the question is it good and is it useful? So in order to convince you that it can be useful, first, I would like to show you what would be the error, what would be the generalization error made by someone who would not use this meta strategy, but who would learn all the tasks in isolations. Okay, so what do we win using this meta strategy? Let us compare with learning in isolation. Well, sorry for the maybe heavy formulas in these slides, but I hope it's quite understandable that here you have the generalization error of task 1. And actually we have the bound that I presented before. It's the best possible 1 plus square root of 1 over, sorry, plus something of the order of 1 square root of n. And then you solve task 2, etc., until the last task, task t, which here again, you obtain the best possible prediction error for this task, plus something of the order of 1 over square root of n. And now let's just sum all these inequalities and divide by t in order to keep means. And you have that over all the tasks, all the observations within each task, your average prediction error is the best average prediction error of the task. You see that here you have an infimum over all possible thetas, because when you sum these infimum, of course, the infimum does not have to be reached for the same theta. As I said, the tasks are different. But the big O here of 1 over square root of n terms, you take the average, it is still big O of 1 over square root of n. So that's what would obtain someone who would not use any meta learning strategy, but you simply fix lambda, that is eta, and the initialization theta 1 once and for all. Now, using our meta strategy, and that was the main contribution of this paper with Dimitri, we obtained the following bound. And I'm going to explain it for a few minutes. But first, just check that this is exactly the same as before. It's the mean of all the predictions in all the tasks. It's as good as the mean of the best error predictions of each task, plus a reminder. So actually, the bounds are the same. It's just the reminder here that is different. So I'm going to compare these reminders. And previously, we had 1 over square root of n. But here we obtain something that is 1 over square root of n, but times this. And what is this? Well, I wrote the formula completely, but actually you see that it's the standard deviations of the thetas. What does it say? It says that, well, if the theta are quite spread, then actually all you know is that they are smaller than b, and you will bound this by a constant, and you will have constant over square root of n, which actually is the same as here, because like the constant is hidden in the big O. On the other hand, if the theta are quite close, one from each other, which means that actually there is some similarity between the tasks, then actually probably it makes sense to start the initialization in the area where all the thetas are and to use a small gradient step. And in this case here, you will have the standard deviations of the thetas that will be quite small. And the limit case, of course, is the case where all the thetas can be the same. That means that all the tasks, even though they are not maybe exactly homogeneous, but you can use the same predictor to solve all the tasks. And in this case, this term becomes 0, which means that you don't have term in 1 over square root of n anymore. And you jump to the second order term that is 1 over n. Okay, so if you had only these 2 terms, that would be a miracle. Of course, there is a third term, and this third term is the price to pay for meta learning. And what does it say? It says that, well, you have to learn to wait for the number of tasks to be large enough so that this third term becomes smaller than this, so that actually you have learned enough information on the hyperparameter so that you reach convergence for the hyperparameters, and so this third term becomes negligible. 2 remarks about this third term. First, we can hope that it's small enough in the sense that the setting we are interested in here is a setting where n is moderately large, actually small even, and the number of tasks is huge. So actually we did not start, and I don't want to pretend this, we did not start by saying that we have huge data sets in each task. It's important to have a very accurate calibration of the hyperparameters precisely when you don't have mini data per task. And so even a slight mistake in the initialization can lead to a problem. So actually, let's consider the case where n is, for example, of the order of 30. On the other hand, as you can expect, you need many tasks to learn through time the hyperparameters. So the moral of this, and I don't claim that this third term is optimal, by the way. My guess is that it can be improved. But this is still a proof of concept that when you have enough tasks, at some point, you can improve by meta-learning over learning in isolation. And I will show you now just some very basic experiments that we made to show you that this is actually the case, so that at some point when t grows, you improve over learning in isolation. So here, actually, we just simulated regression tasks, and all the parameter of the regression task were constrained to be in a small ball, say somewhere here, okay? And we played with the radius of the ball. So in the first experiment here, you see that the radius is 5. And in the second experiment, it's bigger, so the radius is 30. And actually, here, each point in the x-axis is not one data point, it's one task. Okay, so each task, if I remember well, were of about like 20 or 30 observations. And we represent here the average prediction error with the parameters that we have at the end of the task. And actually, what happens? So in black, you have learning in isolation. Which means that you solve each of the tasks without trying to learn the hyperparameters. So you more or less obtain something that is constant actually over time. Each task will come with a problem to learn that will lead to a mistake that is quite large. In red, we implemented a slightly simpler version of what I described before, where actually instead of learning simultaneously here, the gradient step and the initialization, we fixed the gradient step but we learned the initialization only, okay? And then in this case, you can already see an improvement quite fast. Actually, after 25 or 50 tasks, you improve a lot over learning in isolation. And then in green, we implemented the strategy that I just described before, that is learning the gradient step in addition to the initialization. And in the beginning, we were a bit scared because the first thing it does is that it starts by exploding, actually. So the error increased a lot. But after 50 tasks, it starts to decrease. And actually, it decreased even more than learning just the initialization, and we reach something that is much better. So obviously here, you might have the feeling that the improvement of the red of the green over red is not a lot, but remember that we are close to 0, so this is because of the scale. And in the end, like the final mistake of learning in isolation is about 6.5, and still like this is learning the initialization only 0.3, and learning the isolation plus the gradient step, we still divide the error by 2. So this is still quite important. And actually, the other example, even though the scale, the learning times are different, in the end, we have the same result. So with the bigger ball, we still improve a lot with respect to learning in isolation. I would like now to connect the talk to everything MT said before. And in order to do this, first, maybe I should say that there is maybe one word in the name of the team that seems at first unconnected with this talk. So here, in between the nice photo of MT and the nice photos of our complicated equations, we have in between something, I will zoom on it, that's maybe you think I did not talk about. So we can ask the question, where is Bayes in all this? And actually, I hope that you guessed the answer, but you could exactly start the same with a Bayesian algorithm instead of online gradient algorithm. You have data, and here you have a computer that will, so it implements maybe some variational optimization or maybe some Monte Carlo algorithm, and it will produce some posterior. But in order to get the posterior, you need to specify a prior. And that's what the data scientist here is doing with his or her laptop. Proposing a prior, you see. And very often you see that the prior must be based on your prior knowledge, which sounds a bit abstract to me. And sometimes in textbooks it's written, yes, the prior knowledge depends on the experience of the statistician. What experience? But if there is an experience, it means that I can formalize this experience by a learning algorithm. So actually, let's do some meta learning and start with maybe a not so good guess of what is a good prior. But then actually, each time we use Bayesian algorithm to study our data sets, we return a posterior, but in addition, we would like to give some feedback to the next use of the algorithm by saying this prior was good or not. So actually, maybe let's change it. And in the end, I hope to be able to learn an optimal prior. Okay, so this will more obviously be Bayesian and plug within the framework of what the other members of the team are working on now. So just one final slide, actually, to prove you that this is almost already done, actually, at least partially. But this is another paper that I don't think was mentioned before, but a paper that we did with my PhD student, Badreddin Sharif Abdelatif, and with MT, actually, 1.5 years ago. And this paper was actually a study of a variant of the general Bayes principle that MT presented before. I say a variant because we are not exactly able to analyze it in its original form, but still, like, we have a kind of online learning variational inference algorithm that's given here, actually. So instead of minimizing with respect to a parameter, you minimize with respect to a distribution, Q mu. Okay, you minimize the sum of mistakes, and then actually, instead of penalizing, like using penalty on the parameter, we use a penalty that is the Kullback divergence between the distribution and a prior. Okay, so that's an implementation of the Bayesian principle. And actually, it turns out that what we proved in this paper 1.5 years ago is similarly a regret bound. We have a regret bound on the error that is made by the Bayesian algorithm in each task. And this bound takes a similar form to what was seen before. It's an infimum, but here, in addition to the infimum of the possible predictions in the task, you have a reminder that depends on the KL divergence. Okay, so actually you see that almost what we did before for the non-Bayesian algorithm can be done for the Bayesian algorithm. The only thing is that here, at the end of each task, we don't have to optimize the bound with respect to a gradient step and with respect to an initialization, but we have to optimize it maybe with respect to this learning rate, eta, and with respect to, well, the prior pi. That's another kind of initialization, okay? So this would be a general version. But as MT said before, I think that was clearly explained in the first part of MT's talk. You can still interpret gradient descent as or a special case of this Bayes learning rule. And in particular, if you decide that you just use as approximations of the posterior Gaussians with unknown mean, but with fixed variance equal to the identity, for example, then this KL term here between Q mu and pi just becomes actually the norm, the square norm of mu minus m. So it means that actually you obtain exactly the same regret bound that we had before for online gradient algorithm. So in this case, with this very special case of non-very adaptive Bayesian approximation, actually the work I presented before can already be interpreted as Bayesian. But what we want to do now, of course, is to learn priors that would be more interesting. That is like maybe learn the covariance of pi, and then later learn more than Gaussians, but more general distributions. So that's, oh, and by the way, here again, I will just answer to Kibin Sao's question, because you asked the question about adversarial data. At least in the setting of this paper, here again, like the regret bound that we have here is still valid. Well, we have some assumptions on the losses, but we don't have some assumption on the data generating process. So as long as the losses satisfy some boundedness or Lipschitz condition, then actually we have this bound even with adversarial data. That's it. So thank you very much for your attention. Thank you.
Great. Do we want to take the questions and then I conclude? I guess maybe that's a better strategy.
I see two questions related to my talk. So what do you think? Maybe I can answer now. I try to be brief. Okay, sure.
There were three, but then there was a good question. But it's
okay. And that's a question that disappeared actually, or maybe I pushed on the wrong button. But there was yes, sorry. Does meta strategy similar to implicit MAML? Yes, I mean, like, of course, MAML is an example of a meta strategy that is in practice much better than ours because it is very clever and very well tuned. But the problem is that, to my knowledge, they don't have such a theoretical analysis. So actually, ideally, we would have liked to be able to provide a theoretical analysis of MAML, but what we did instead was to first start with a proof of concept and to prove a regret bound for a very simplified version. But the idea remains the same. So that's basically it.
But I also think that maybe in MAML, I don't know about implicit MAML, but they're using this train test split, right? And I think you don't have that in yours, right?
So indeed. So the point is that, of course, when you use a test set, you expect that if you train your algorithm on a learning set and then you test it on a train set, you hope that actually what happens on the train set is a good idea of the generalization. In my case, instead, in order to prove nice theorems, like we used a generalization error bound. Maybe it's slightly more theoretically sound. On the other hand, it's a bit more pessimistic as well because the bound is not an estimate of the generalization error. It's slightly above. But yes, I mean, the idea remains the same, I think. It's to try to replace what you see on the data by a generalization. What hyperparameters, a question by Kibin, can you explain about what parameters you can include? For example, architecture of DNA and number of layers, width of layers or learning rate. Of course, in the framework I presented, none of that. It's too ambitious. Ideally, of course, I would like to. It's something that we can think about, like especially like, for example, number of layers. It's something that can be incorporated in a prior. And then actually we can learn, by learning the prior, we can hope that this will work. At least I must say that at some point, in some time, it's the kind of things I would like to try through experiments. But definitely, our first paper on Bayesian meta-learning, or learning the prior through many different tasks, we'll start by much simpler thing. We'll start with learning like Gaussian distributions for linear regression, logistic regression, and if we can, maybe 2 layers neural network. And at some point, maybe we'll try to think about more ambitious things, but we'll start with simpler things. And then there is another question in the main theorem of the bound. Sorry, actually, maybe I should have answered this one live, but on the bound loss function, why the error bound is smaller when the number of tasks increase? Can you give an intuitive explanations? Yes, actually I can. So I will come back to something actually that I realized actually. It's a question that did not come, but maybe, I mean, even myself, I just realized that there's something weird actually in this slide here. I say that I'm going to learn the hyperparameter lambda because no one knows what lambda should be. And then actually in this meta strategy, I have an hyperparameter alpha. And what alpha should be? The answer is that actually, depending on how we calibrate alpha, we still have this convergence. In some sense, the calibration of alpha is a third order term. But actually, this is where this is connected to Quibin's question, actually. Why? Because actually, by doing this, we are solving an online optimization problem on lambda. And for this online optimization problem, we also have a regret bound. And I did not write the regret bound in full generality, but when we make it explicit, it becomes the term here in n over square root of t. Maybe if you just give me 1 second, I can take from the paper, even though like I should not show, I'm not allowed to show that it's written in a bicolumn format, but anyway. From the paper, actually, we have kind of very general meta regret bound, if I can find it somewhere. It's given here, actually. So it says that the meta learning error, that is the sum of all the possible errors, is the sum of the minimum bounds that I had before, plus a term that is exactly very similar to online gradients, because actually I'm applying the same kind of idea, but at the meta level. And then when you solve this term, by taking alpha just at the right order of magnitude, then actually this makes this term in square root of t appear. So actually this is where it comes from. And even though it might not be optimal, such a term has to be here because there is a price to pay for learning the hyperparameter.
There is another question for you after that.
Oh, okay, yes, I see actually another question. Once you learn a set of tasks, a lot of theta I, how do you achieve update of theta? There is a sequence of thetas. Does it create a sequence of gradients updates, or each task updates theta at each iteration? Okay, I will come back maybe to the slides here. Okay, so I hope, maybe this, yes. What I described here is just what happens within one task. So within each task, I mean, remember that the tasks are not generated by the same process, and the tasks might be different. So each task can be trying to predict a different variable, for example. So the tasks don't have the same optimal parameter. So within each task, think about just learning the task in isolation. You want to learn one parameter that is theta, for example, your regression parameter. You start from an initial guess in your gradient descent. You follow the gradient, online gradient descent algorithm. But when you reach the end of the task, this task is considered as solved. And you will start a new task, okay, which can have a completely different parameter. So this sequence of theta at that time would be, you just throw it away. The only relevant information that you want to keep in this context actually is the hyperparameters. So there is no, like the tasks are generated, the parameters actually are generated according to this formula here, but you see that the recursion is only over I. So you can forget about T actually, you can just think about one task. You just have an index and a recursion over the number of the observation, But when you reach the end of the task, we restart the process. So we don't keep the sequence of the theta. So I hope I understood the question well. I mean, if it's not the case, I will be happy to talk with you later about it. So don't hesitate to contact me. And I think that the next question is more related to your talk, MT.
Yes. So yeah, I think Dharmesh is having some technical problems and is not shown here, but yeah. Okay, Dharmesh,
I
so
think it's fine
this
actually now for me. Sorry.
Oh, great, you could talk. Awesome. So the question is memorable data of MNIST. It's a question about that in the NeurIPS 2019 paper. The memorable data for MNIST looks like outliers. Do we really need to memorize them instead of ignoring them? I think this is a wonderful question. And maybe I'll just say some words, Ramesh, and if you have something to add, feel free to say it. So from what I think is that this is a very good question, actually, that there are, two types of problems that can happen. So there are examples that are right at the edge of our knowledge, the examples that we want to learn about or we want to go beyond. But there are also examples that are beyond the edge and might be something that we're not interested in. So they might be outliers. And in the criteria that Dharmesh talked about, there is residual and there is leverage score. So if you look at examples that have high residual, many of them would be something that the model is not able to classify well. And you would think of them as outliers. But leverage score is trying to get you to the boundary of that. So you could take the axis of data points and you could say there are data points that are classified very well. And for those points, both residual and leverage is small. Then there are data points that are classified really badly and residual is very high, but leverage is small. And they are basically outliers. And then there are points that are at the boundary of those for which the leverage score is high. And that might be important for exploration. It's a little bit more complicated to think about it, but as Dharmesh said, that this is really depends on application of which one is the outlier and which one is the point at the edge of the knowledge. So so you have to kind of think about it depending on what you're going to do with it. Would you like to add something, Dharmesh?
Sure, I guess. Yeah. So I mentioned at the end of my presentation this experiment where I was removing data. And so there we tested examples by the leverage score. And if you remove those examples from a data set and retrain, model performance did drop quite considerably. And so this indicates that those examples were the most important ones to actually classify the test set well. You asked about the memorable data of MNIST in particular, and those were taken from the front paper, which they used lambdas. So these points here were along the decision boundary. And so you could say that, yes, there's some ambiguity of their class because they lie at the very boundary between classes. But in that case, the application was about maintaining the boundary as moving to new tasks, which is what you want. Of course, if you are thinking about more data cleansing or sort of extracting a kind of core set that represents the kind of class very well, then perhaps that wouldn't be the most appropriate thing in that case. And you would want perhaps the less memorable ones, like ones that we called had a small value of lambda, which were very typical, very regular of the class. So it very much depends upon what application you have in mind.
Great. That's yeah. So this is a very good question, actually, and it's kind of a $1 million question in terms of knowledge representation and knowledge transfer, because it's very hard to know beforehand how you should go about it. Okay, great. It seems that there are no more questions, and so I will try to just close the seminar by giving a few final words about what we are doing. So, okay, so as you saw in this seminar, we started, with uncertainty and then showing how if you start with thinking about the uncertainty or distributions for parameters, naturally things that don't include distribution turn out to be a special case of this. So this is kind of a more general way of thinking about problems. And then in our current work, we're trying to show that these distributions, they help us to do knowledge representation and knowledge transfer, where Dharmesh talked about how you can derive these dual variables from the solutions of the base objectives. And then I was showing how you can use it in continual learning. And then Pierre talked about how these kind of settings lead to these regret bounds, generalization error bounds that are inherently of Bayesian nature. So the group is really focusing now on using these principles and these ideas for a variety of tasks. You've already kind of seen papers on continual learning and the talk that I gave, but we are actually and Pierre talked about meta learning, and even though it was a good joke, even though it doesn't seem very Bayesian, but the way that we actually are thinking about all this problem, it really comes from Bayesian principles. So we're working on like active learning, online learning, meta learning, reinforcement learning, federated learning, on all these topics. And we're also kind of looking for partners to work on explainable and interpretable. You could see like the memorable experience idea is really going towards how you can interpret what the knowledge the model has actually learned and how to represent it. And then it's used in kind of doing reasoning and understanding cause and effect in the data. Um, and the I just wanted to end the seminar with a big picture view of this. So you see that we start in this Bayesian principle from uncertainty, and then we go to learning, and then we go to knowledge. And this is really, it's fundamentally different from the way that the machine learning actually runs right now. So in deep learning, for example, first step is to say, well, let's collect a lot of data. So the focus is on knowledge. Somehow we assume that the data is knowledge and data has everything, and that's all if we collect more of it, then our learning will be better. So uncertainty comes as a last step. Like once you have collected the data, then you have learned everything, then you think about uncertainty. But really, it's the wrong approach because your data might be completely wrong, or you might be collecting data at the wrong place, or your model might be heavily biased. You don't know what exactly you have learned. And then thinking about uncertainty really is kind of like first, you have created the problem and now you're trying to solve it. The Bayesian perspective is really going from uncertainty, so starting from thinking about the data, fitting it well, but also thinking about the gaps between the data, the things that you haven't observed, the things that will come back to bite you in the future. And if you start from uncertainty, then you see that learning actually naturally everything where you ignore this uncertainty, there are special cases of it. But if you start to add uncertainty, then you can get a better idea of knowledge. And that's basically how we went in this talk. Now, why I think that this is the way that things should be done is because, you know, current machine learning, when we really fit models to the data, it's really about what do we know? It's about I have some data in hand and I know certain information about the world and I fit a model. And so that tells me what do I know. But it really doesn't tell me the more important things. So like, what do I not know? Where have I not collected data well? And which part of the world I haven't seen enough? What kind of skills I'm lacking in the world to that I should be, knowing about? And that question is the question about uncertainty. And that's a much harder question. And what we're really doing is that we're saying that there is something in between, which is about, well, I don't know about many things in the world, but I really don't have to worry about that. Like kids, they don't worry about like, learning calculus where they say, when they're learning like how to add numbers, they don't have to worry about calculus. They only have to worry about things that they need to know in the next grade, right? So what do we need to know and how do we identify that? And that's where our work is sort of focused now. So we believe that to be able to understand what do we need to know, it actually goes into this knowledge representation, knowledge collections, knowledge transfer from what we knew before to what we are learning now. And the posterior approximation really lets you do this because the models are representation of the world in terms of what you have seen so far. So you haven't seen everything. But posterior approximation is trying to kind of go, inside the model and trying to understand why do we know what do we know? What experiences have I had before that makes me the person that I am? And this is really the idea of memorable experience that we presented is in kind of instance that comes from it. Okay. And so what we are really banking on right now is that all of this kind of dual thing that I showed you, the principle, Bayesian principle, and this dual vectors that we derive from it, they will somehow help us to represent the knowledge. So memorable experience was an example, and help us to transfer this knowledge. And the continual learning was an example that I showed. And then also to collect new things in the world based on the uncertainty that we have. Right? So this is the work that we are actually really focusing on doing reinforcement learning and active learning and meta learning and online learning and other kind of things. Okay, so I hope that this seminar gives you a sense of what our group is working on right now. So if you're interested in checking out more about the group's work, I encourage you to follow us on Twitter or go check out the webpage. In the future, we are hoping that the rest of the members of the group would also give this kind of seminar. So encourage you to attend that. And if you have any questions, please feel free to email us and ask us more about our research. And we really thank you to attend today's seminar. And I also want to thank the other speakers today. So maybe Dharmesh and Pia, can you come online? All right. So thanks to the wonderful speakers. Thanks to the Recon AIP team to help us with the support of this webinar, and helps to Chibin for actually organizing these open seminars. Thanks a lot.